Muskan Singla from PU Chandigarh, and she attended level O in MTTS 2022. She will speak on an introduction to CLT groups. Muskan.
So, hi everyone. Myself Muskan Singla from Punjab University, Chandigarh. I have attended MTTS Level O, and my topic for today's talk is an introduction to CLT groups. So, starting from a very well-known theorem in group theory, that is Lagrange's theorem. It states that order of a subgroup of a finite group divides the order of that group. That is, if H is a subgroup of a finite group G, then order of G is divisible by order of H. So my question was, is the converse true? And the answer to this inverse of Lagrange's theorem is not true in general. That is, if D is a divisor of order of group G, then there may not exist a subgroup H of G such that order of H is equal to D. So I asked examples. Someone was giving examples.
Muskan, we see the group A4 alternating group on 4 elements. The
Yes.
order of the group is 12. But if we will see the divisors will be 1, 2, 3, 4, 6, 12. But we see that the subgroup of order 6 is. So it is how it the converse become uh,
False.
true.
Converse is
False,
not
sorry.
true in that case. Yes,
Yeah,
you are
oh
right.
sorry.
So this is my example, which is consider group order 12, and here converse does not hold true. And let me prove this. So by assuming H is a subgroup of A4 and order of H is 6. So we know that the index of H in G will be 12 by 6, that is 2. And we also know that a subgroup with index 2 is always normal in its group. So there will exist a quotient group that is G by H with order 2. So for all elements in A, all elements in G, suppose A is any element in G, we will have AH, order of AH is equal to 2. So AH square is equal to H only. So this will give me the result that A square H is equal to H, which implies that A square belongs to H. Hence, I arrived to a conclusion that for all A in G, we have A square in H, which is a separate result also, but we are using it in this proof. So moving on next, we know that there are 8 3 cycles in A4, right? So there exist at least one 3 cycle in H. We can prove this also. So let us suppose S is a 3 cycle. So we know that as S is a 3 cycle, so order of S will be 3. And I can also write S as S square whole square. So SH is equal to S square ka whole square n to H, which means that coset. So as I know that for every element A in G, A square belongs to H. So this will be equal to H only. So SH is equal to H, which implies that S belongs to H. So I have proved that S is a 3 cycle and it belongs to H. But we know that if a normal subgroup contains at least one 3 cycle, so all the 3 cycles that are 8 in number here will be in that normal subgroup. So I arrived to a conclusion that H will contain 8 3 cycles. But this is a contradiction to the fact that order of H is 6. So I have proved that here there is no subgroup of order 6 in A4. That is my contradiction to the Lagrange converse of Lagrange's theorem. So we have we can classify the groups in some way like no, like this, where the converse holds and where the converse does not hold. So there are groups named as CLT groups, which are, wait a minute. which can have finite group which satisfies the converse of Lagrange's theorem completely. So a group is called a CLT group if there exists a subgroup H of G of order D for each divisor of order of G. So here are some examples. I have G is equal to Z6, that is integer modulo n group. So order of G is 6 and divisors of 6 are 1, 2, 3 and 6. And H1 is equal to identity only, singleton identity. This is a subgroup of G with order 1. H2 is a subgroup of order G containing 0 and 3 with order 2. Similarly, H3 is a subgroup of G containing 0, 2 and 4 with order 3. And H4 with order 6 is completely Z6 itself. Similarly, I have another example, G is equal to V4, containing the cycle identity 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. And order of G is 4. Divisors of 4 are 1, 2, and 4. H1 is equal to only identity group, that is, order of H1 is 1. Next, I have H2 is equal to singleton, sorry, H2 is equal to identity cycle 1, 2, 3, 4, and H2's order is 2. Similarly, order of H3 and H4 is also 2. These are two another examples. Again, next, H5 is equal to V4 with order 4. So here, in both these examples, the converse is holding completely true. So these both groups are CLT groups. So I have another example also, which is S4, the symmetric group. So order of this group is 24 and divisors of 24 are 1, 2, 3, 4, 6, 8, 12 and 24. So I have different subgroups with different orders. Starting with order 1, I have the identity group containing only identity. So next with order 2, I have H is equal to the identity cycle, then cycle 1, 2. Then with order 3, I have subgroup uh, identity cycle, then 1, 2, 3, 1, 2. Next is if order of H is equal to 4, I have another subgroup with order 4, that is identity cycle, then 1, 2, 3, 4, then 1, 3, 2, 4, then 1, 4, 3, 2. Next, a subgroup of order 6 is given as identity cycle 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2, which is S3 itself. We can also see this. And we know that S3 is a subgroup of S4. We can directly see this. Now, next with order 8, I have identity cycle 1, 2, 3, 4, 1, 3, 4, 1, 4, 3, 2, then 1, 2, 3, 4, which is product of 20. Then another product which is 1, 4, 2, 3. Next is 1, 3, 2, 4. Now, next subgroup with order 12 is A4. And subgroup of order 24 is S4 itself. Now, the question is subgroup of a CLT group is CLT or not? We can see it clearly now very easily that it is not true because S4, I have given example that S4 is a CLT group, but we have also proved in previous slides that A4 is not a CLT group, and we know that A4 is a subgroup of S4. So here we have an example where S4 is a CLT group, but A4 is not a CLT group. So I have some another results, which are cyclic groups are CLT groups. So let us suppose that G is a cyclic group generated by element X, where X belongs to G, and order of that group G is n. Let D is a divisor of n, which means D divides n. So there exists some m belonging to integers such that n is equal to dm. Now we know that uh, order of g is n and it is generated by x. So order of x will also be n. So x raised to power n is equal to identity. So it implies that x to power will also identity. Now I can write this as x raised to power m raised to power d is equal to identity. Hence, we found a subgroup H generated by x raised to power m of g such that order of H is equal to d. So I can find subgroups of for each divisor of n. Hence, G is a CLT group. So we can conclude that every cyclic group is a CLT group. Okay. So my next result is direct product of CLT groups to a CLT group. So I'll be proving firstly G1 and G2 are CLT groups such that order of G1 is equal to N1 or equal to N2. Then order of the direct product of G1 and G2 will be N1 and 2. Now, what I have to prove that there exists a subgroup of G1 cross G2 such that its order divides N1 and 2. So let us suppose A divides N1 and 2. Now, if A divides N1 and 2, I know that there will exist A1, A2 belonging to Z such that A is equal to A1 A2 and A1 divides N1 and A2 divides N2. So now I know that G1 and G2 are CLT groups. So for every divisor of order of these CLT groups, there will exist some subgroup of that divisor of that order divisor. So there exists H1 subgroup of G1 and subgroup of G2 such that order of H1 is equal to A1 and order of H2 is equal to A2. So order of H1 cross H2 will be equal to A1 A2, which is A itself. So I know that H1 cross H2 is a subgroup of G1 cross G2 as H1 is a subgroup of G1 and H2 is a subgroup of G2. So I have found the subgroup of order A of the group G1 cross G2 where A divides the order of G1 cross G2 which was N1 and 2. Hence the result uh, holds for two CLT groups. Now I proved that G1 cross G2 is a CLT group. Now I'll prove it in general. I'll prove this by induction. Let me assume that G1, G2 up to Gn plus 1 are CLT groups. So by induction, assume that product up to n is a CLT group. That is G1 cross G2 cross up to Gn is a CLT group. Now I know that cross product up to n plus 1 is equal to cross product up to n cross Gn plus 1. So, which is again a direct product of two CLT groups. I have assumed that product up to n is a CLT group and Gn plus 1 I already knew that it is a CLT group. So again we got a direct product of CLT groups and I have also proved that product of two CLT groups is a CLT group. So I also proved by induction that in general this result holds true. So direct product of CLT groups is a CLT group in general for any n in natural numbers. So my next result is abelian groups are CLT groups. Now everyone is familiar with fundamental theorem of abelian groups. So I'll be using this in the proof. Now let G be an abelian. According to fundamental theorem of finite and abelian groups, a finite abelian group is isomorphic to a direct product of cyclic groups of prime power order, where the decomposition is unique up to the order in which the factors are written. And we already have proved in our result 1 that cyclic groups are CLT groups. And in the result 2, I had proved that direct product of CLT groups is also CLT. So I directly arrived to the conclusion that abelian groups are CLT groups. So is my argument convincing everyone?
I think you mean finite abelian groups, right?
Yes. CLT groups are defined on finite groups only. So now I'll be discussing about different groups up to order 11. Firstly, considering for groups of order 2, 3, 5, 7, and 11. As these are prime, so I know that only one type of group is present, and we have already proved above that cyclic groups are CLT groups. So I directly got that groups of order 2, 3, 5, and 7 and 11 are CLT groups. Next, moving on to groups of order p square, where p is prime. We know that p square groups with order p square are abelian groups, and these will be also CLT groups. So groups with order 4 and 9 are CLT groups. Rest I'm left with groups of order 6, 8, and 10. Now, first considering about groups of order 6, equal to 3. So, two groups are possible of order 6. One is abelian and other is non-abelian. And the one which is abelian will be isomorphic to Z6, with where Z6 is a cyclic group. We already know that, and cyclic, hence it is CLT group. Next, second, G2, which is isomorphic to D3, which is a non-abelian group, and it consists of three rotations and three reflections. So a subgroup with order 1 is again a singleton group with identity only. Group with order 2 contains subgroup with order 2 contains identity and S, where S is a reflection with order 2. Next, subgroup with order 3 contains identity R and R square. And subgroup with order 6 is D3 itself. So we got that G2 is a CLT group. So we arrived at the conclusion that every group of order 6 is a CLT group. Next, moving on to groups of order 8, which is 2 cubed. 5 groups are possible of order 8, 3 of which are abelian and other 2 are non-abelian. And we know that abelian groups are always CLT groups, hence all the 3 abelian groups mentioned below are CLT groups. So first abelian group is isomorphic to Z8, second one is Z4 cross Z2, third one is Z2 cross Z2. So next, two non-abelian groups left are, first one is D4, which is again a dihedral group. It contains 4 reflections and 4 rotations. So a subgroup with order 1 contains identity only. A subgroup with order 2 contains identity and S, where S is a reflection. And group of order 4, subgroup of order 4 contains identity R, R square, and R cube. Again, subgroup of order 8 is D for itself. So here again, I found subgroups of all the possible divisors of 8. Next possible type of group of order 8 is Q8, which contains plus minus 1, plus minus I, plus minus j, and plus minus k. Now, subgroup of order 1 contains identity only. Subgroup of order 2 contains plus minus. Subgroup of order 4 contains plus minus 1 and plus minus I. Subgroup of order 8 is again Q8 itself. Here again, I found that Q8 is a CLT group. So all the possible types, all the 5 possible types of group of order CLT groups. Hence, again, group of order 8 is a CLT group. Next, the last one, which is group of order 10. We have two types of groups of order 10. One is abelian and other one is non-abelian, as similar group of order 6. So first one is isomorphic to Z10, which is a cyclic group, and which implies that G1 is a CLT group. Next, second one, again similarly as order 6, G2 is isomorphic to D5, which is a dihedral group containing 5 rotations and 5 reflections. So, with order 1 contains identity only. Subgroup with order 2, H2 contains identity and S, where S is a reflection. So, my next subgroup of order 5 contains all the rotations of R1, R2, R cube, and R4. Next, subgroup of order 10 is D5 itself again. So this is also a CLT group. Hence, I proved that again group of order 10 it may be of any type. It is a CLT group. So we have seen that all possible groups of order up to 11 are CLT groups. And from 12, we found that A4 is the smallest group of order 12, which is not a CLT group. So thank you. And a question I can we all can think of is that here I discussed about CLT groups, that there may be some groups where the converse is holding true. So we can also, where the converse is not holding true, can we also guarantee some subgroups of some particular type of order? Can we guarantee? So this is my question for you all that you might think of. So thank you. This is all from my side. Any
Thank you,
doubt you
Muskan.
can ask.
Any comments or doubt? Comments, questions? Okay, so if there are no more comments, doubts, let us thank the speaker. Uh, it was really a nice talk.